me start the recorder. What I do, I record every class. I don't recall taking the roll sheet, but yeah. So at the point I start to record everything in the class. It's a program called Screencast-O-Matic. It's now recording. You can't see it, but as soon as it comes up, you'll see what's being recorded. You can hear my voice and see whatever is projected on the screen. What you can't see is my pointing to it. That doesn't do. It's just what's projected on the screen. Now, as soon as class is over, I'll upload it to YouTube. It usually takes about an hour or so to do that, but then sometime later, probably the end of the day, like 5:45 today, because I have class all day on Tuesday and Thursday, I'll finally assign that upload to YouTube to a playlist. And the playlist you can access through Blackboard. Okay, so have you fiddled with the new Blackboard yet? Okay, so you know, okay. So in the new Blackboard, the first thing you see when you get to this class is the syllabus. I think that's up to date. Okay? The next thing you see is my locator card. And by the way, have you figured out how to open those things? Any of those files. You have the 3 dots you have to click on and upload. Yeah. And let me see if I can remember your name. Ian. Right. Okay. All right. So you know how to open those. So there'll be the syllabus, locator card that shows when I'm on campus, off campus, in class, out of class, which campus I'm on, that kind of stuff. Okay. Then there's the research paper instructions. Okay. Then there's, I can't remember the order. Somewhere down there you'll see the course key for this class. Now that's if you're doing one of the e-books, in order to access it, I think they give you so many days free. With that course key, you can do it. Now, it also gives you access to all the websites. I've got them out there, but I don't ever require those. Those are just extra practice that you can do, and WebAssign has some tutorial help. So if you're stuck on something, use that, and see if you can, get the benefit out of it. The reason I don't use WebAssign, when I've tried to use it before in the past, I spend more time with my students saying, no, you did get the right answer. It's just it only recognizes one way to write that answer. And it's just really frustrating to me and really frustrating to the students. Because if you could write it as 1/2 x, but it wants you to write x over 2, it'll tell you 1/2 x is wrong. And it's not wrong. It's perfectly correct. So that's why I don't use WebAssign. But you can use it. It's there for your viewing enjoyment. Okay? Let me see, is this Nikhil?
Yes, sir.
Okay. Did I pronounce it right?
Yes, sir.
Okay. All right, good deal. Okay. So that key is there. And it says class key. You don't need the word class key. All you need is, it starts with Lawson, not Larson, Larson's the author, Lawson.al, and then there's a space with 4 digits and another space with 4 digits. That's the key. Be sure you put the spaces in there and the dot in there. But the word class key or course key or what, you don't need. Okay, so that's there. Then somewhere after that, and I can't remember which order, is the YouTube videos. And when you click on that, you don't have to do anything else. It comes to the YouTube videos open up. Now what you'll see is a whole bunch of videos. You say, you can't have done that many this term. No, I didn't. Those are videos from the last time I taught the course. And what I do, the older ones are at the top, the newest ones are at the bottom. So if you go to that and look at the YouTube videos, the first one I think is named Syllabus, and I don't remember what the next one named, but those at the bottom are that. As soon as I record something this term that replaces something last term, I put it in here and it shows up at the bottom, then I go up and delete the one at the top. So basically you always have the whole course there. Now the reason I leave those up there, it has happened before and it will probably happen again. Something screws up. My computer may mess up, the server may mess up, Screencast-O-Matic may mess up, something may mess up, and I won't be able to record one day. So you'll always have something pretty close to what we're doing out there. And so you do that. And it could happen, it has happened before, that Jafari shows up. No, I'm sorry, that was, okay? There is a good chance we're going to miss at least one class, okay? Because I have a mild form of leukemia, and my hematologist only sees patients on Tuesday mornings, okay? And I do have an appointment coming up either in March or April, I don't remember when, but I'll let you know plenty of time. And on that day, I almost guarantee you we'll miss this class. And then we'll decide whether you want to make up the class or use the previous YouTube videos. So that's where it might come in. There is about a 50-50 chance I may miss another class. I think I told y'all this before. Last week I turned 69, okay? And that means next year at this time I will be 70. And that's about time to say, that's all, folks, you know. And so I'll be retiring, I think, next year about this time. So in the teacher retirement system, they want you to attend the seminar on how to navigate the retirement system. And those are all-day seminars, and they ask for 2 choices, so I put the March 4th or 5th. The thing that aggravates the fool out of me is that they don't give you any options for a Friday. They're always Wednesday or Thursday. So it's a 50-50 shot whether they're going to assign me to Wednesday or to Thursday. If it's Thursday, we'll miss this class because those are all-day seminars. So I may miss that one too. But if they assign me Wednesday, then we won't miss that class. So that would be another opportunity that we might, you might be able to use the video that's already out there rather than one that we'll talk about that and talk about it later. Okay, so after the YouTube videos, somewhere in there is the things like the syllabus and things like this that are actually documents, they have a little, it looks like an 8.5 by 11 piece of paper with something on it that means it's a document. Those that are web links, like the YouTube video, instead of it looks like this, but then it has links like a chain. That means it's a web link. Then there's one that's like this, and it looks like a folder, a file folder, okay? That one is a folder, okay? And that will be called PowerPoints, and there's where every section PowerPoint that we will conceivably do in this class, probably more than we'll do, are in that. So if you want to look at the PowerPoints ahead of time, you can. If you want to print them off to take notes on, you can. Whatever you want to do with them, but they're out there, okay? And then there are a few other web links, those kinds of symbols, of files that are sites that either students have told me about or I found myself and thought you might find useful for the course. So that's a quick and dirty of what's out there. So if you want to know what we did in the first 2 classes, go to the YouTube videos, you go to the bottom, and the first one is entitled Syllabus. I don't remember what the second one is entitled, but those 2 at the bottom, those are what we did the first 2 days of class. And I've been recording all this, okay? This will be on the 3rd day of class. All right. Any questions on what we've done so far? All right. We did get started last time in 4.1. This pre-calculus trig, you use the same book you did for pre-calculus algebra, only we use chapters 4, 5, and 6. That's it. Chapter 4 is a long chapter. 8 sections, and every section is long. So we'll have a test at the end of the first 4 sections, and then another test at the end of the next one. After that, chapter 5 and chapter 6 will have their own tests. Okay. So we're in 4.1 right now. We're on page 262 if you do have a book and are following along. And we're right past the middle of the page. We had done example 1, which is what you see on the slide here. So let's go from current slide here. We had done example 1. It had an A and a B part. This was the B part. That's the result of the B part. Here's where we're picking off today. Okay? So any questions or anything we've done up to now? there are two sets of angles, okay, that have special relationships. Two positive angles, that means angles going in counterclockwise direction, two positive angles, alpha and beta. Remember, we usually use Greek symbols to represent angles. Occasionally we'll use capital letters, but usually Greek symbols. These two positive angles are complementary. Now, what word do you almost see in that? Complete. Okay. I think the Greeks named this. To them, or if I said this, what angle am I representing? A right angle. Okay. Now, why is it called a right angle? Wouldn't it be a left angle? No. Okay. What the Greeks meant by it, they thought that was the perfect angle. Because a right angle gives you the most strength in a building. Most floors and ceilings are at right angles. Your floors and walls are at right angles. That's your greatest strength. If this wall was leaning, I don't want to be under it. Okay, I want it to be 90 degrees. If it's leaning out that way, I'm not going to bump into it because it doesn't seem as strong. Okay, so they considered a 90-degree angle or a high halves angle to be a right or perfect angle. So two angles are complementary or complete each other when they add to be their complements of each other, complete each other when their sum is pi halves. This is radian, that's 90 degrees in degree. We haven't done degrees yet. We're dealing strictly in radians. And if you don't remember or don't know what a radian is, go back and listen to the YouTube video. We went through that last time. Okay. Now, there's another special two angles. Two positive angles are supplementary when they supplement each other when they form not a right angle, but a straight angle. In other words, they form a straight line. So here's what it means. This alpha plus that beta had to be a right angle. Okay? These two, alpha and beta, they had to be pi angle. This is pi halves, this is pi. Okay? And they add to be pi. Now, based on this, what do both alpha and beta have to be? And we haven't actually used this term yet, but I just wondered if you... Say again? Acute angles, perfect, meaning less than 90 degrees. Because if they're both positive, they add to pi halves, or 90 degrees, they have to be less than 90, okay? If they're both positive and they add to pi halves, they must both be less than pi halves. So those are both acute angles. How about that pair? Both positive angles. If one is acute, the other one's obtuse. You got it, okay? Now, the only exception to that, if alpha and beta were both right angles, then they need to be acute or obtuse. So the two right angles would be supplementary. Okay. Most of the time, one's acute, one's obtuse. And these two, they both have to be acute because they both have to be positive. Okay. Does that make sense? All right. Now, they're skipping example 2. So let's go back, see if we can find any white space to do example 2. I don't see any on here. But let's do it here. All right. Or actually closer would be here. Let's do it here. Example 2. What is the complement? And by the way, this is a tablet computer, meaning I have an ionizing pen I can write on the screen. If that's projected on the board, that's also saved in YouTube video. Again, my waving at it and pointing at it, that's not saved, but anything that shows up on the screen is saved. So they say the complement of 2 pi fifths, or 2/5 pi, or however you want to say this, how would you get that? What is the complement of 2/5 pi? What What is it that makes two complementary angles?
So would it make two complementary angles?
Right. What has to be true of two complementary angles?
That's two acute angles.
The what?
Two acute angles.
Okay, they have to be both acute angles. You're absolutely right. Is 2/5 pi acute? Yes, they're less than half a pi. 2/5 is less than half a pi. And even David is here. Okay. So we're only missing Amari and Austin. Okay. Austin, I won't see that frequently because he works during the day. They either canceled or he couldn't do the evening section, so he's having to do it remotely. So he gets in touch with me anytime he has a question. Okay. So 2/5 pi is an acute angle, so it does have a complementary angle. We need to figure out what it is. Any ideas how to get there?
I guess first you got to figure out what degree angle is 2/5 pi.
Okay. Let's stay with radian measures, but let's see. What is the complement of 2/5 pi? So let's let this be, let's give it one of those Greek letter names. What's going to be the angle you're looking for? Say again? Don't use pi, that's a number. Alpha, why not? Let alpha equal the complement. Okay, so that's going to answer that question. Let alpha be the answer. Okay? Now what must be true of alpha and 2/5 pi? Say again? Pi, they have to add to be pi over 2. So alpha plus 2/5 pi has to be pi halves. Do you agree with that? Okay. Now, there's an equation. There's your unknown. The sad news is it has fractions in it. Now, I'm kind of with Ian, right? Not Aaron. With Aaron, that's right. You're Ian, okay? Sort of with Aaron here, I'd rather get it in degrees and it makes it much easier to do. But we're stuck with radians here, so let's deal with it. How do you deal with an equation that has fractional form? The common denominator. What's your common denominator of all those denominators in that equation? 10. What do you do with that 10? Okay, not divide. Multiply that 10 by every term on both sides of that equation. Okay? What you've done is just multiplied the same thing on both sides of the equation. That means we haven't changed the value of the equation, just how it looks. Okay, so this would be 10 alpha, and 5 will go into 10 how many times? 2 times. And 2 times 2 pi would be 4 pi is equal to, and here 2 will go into 10 5 times. That would equal 5 pi. Agree with that? Okay, we want to figure out what is alpha. Where's alpha? Oh, what? Never mind. Okay. So let's subtract 4 pi from both sides. These go to 0, and you get 10 alpha is equal to what? Pi. Okay? And then if we want to know what alpha is, what do we do? Divide by 10. Both sides by 10, and there you have it. Alpha is equal to pi tenths. Okay? How do you check that? Pi tenths plus, okay, let's get that in tenths. That would be 4 tenths pi, right? 2/5 pi, 4 tenths pi. So 1 tenth pi plus 4 tenths pi is 5 tenths pi, 5 tenths pi is pi tenths. Done. Make sense? Good old fractions, we love them, don't we? Okay. So, that's the A part. No, it isn't. Okay, that's the first half of the A part. The second half of the A part says what is the supplement of 2/5 pi. What's going to be true of the answer to that? Yes, the sum of the supplement plus this is going to be 2 pi. So you want to call it alpha again, or you want a different? Okay, we'll do alpha. Alpha plus 2/5 pi has to equal what you say? Not 2 pi. Pi. Okay. Eat just 1 pi at a time. Okay, never mind. Okay, now. Can anyone just look at that and tell me the answer, or we can do the math on it? Second? Oh, I thought someone said something. What alpha would make that equation true? 3/5 pi. You're absolutely right. Because you can subtract 2/5 pi from, this will be pi is 5/5 pi. Okay. And this goes to 0. Alpha equal 3/5 pi. Now, back up just a little further. Pi tenths is certainly an acute angle, right? And 3/5 pi is obtuse because the 2/5 pi is acute. Okay? Remember, anytime you have supplementary angle, most of the time one's going to be acute and one's obtuse. These both have to be acute. Verify that. Okay, good deal. That was example 2A. Ready to all right, okay, I couldn't find the question on the next one. You want to do the B part? I don't like the way they did them in the book, so we're doing them this way. If you like the way they did them in the book, you can do it this way. The B part said, what about 4/5 pi? What is the complement of 4/5 pi? Any ideas? Any thoughts? Anything disturbing? Second? Yeah, it would have to be negative, but what's the definition of complementary angles? They both have to be positive. So 4/5 pi does not have a complement. Why not? It's obtuse. It's greater than pi halves. So it can't have, there is no positive angle. You can add something greater than pi halves to give you pi halves. So no complement. Okay. You could either picked up on that by looking at it. Now, how about this one? What is a supplement of 4/5 pi? That's the first question. Does it have one? Say again? What's your thoughts on it? Okay, yeah, it would have one, but it has to be an acute angle. What would it be? Second? 1/5 pi. Supplement of 4/5 pi is 1/5 pi, pi fifths. Because 4/5 pi plus 1/5 pi is 5/5 pi, that's pi. Okay, perfect. Y'all are good at this. Now, I said this on example 1, but not everybody was here. Example 2, and after every example in the text, there is something called the checkpoint. And the checkpoint asks similar questions to what that example did, And if you know the answer, you're confident in the answer, do it and then move on. But if you're not certain about it, you can go to larsonprecalculus.com and get an audio video solution for that. Every checkpoint in the book. And if you recall, I said that this author, I mean, most pre-calculus books are the same. I mean, there's not a dime's worth of difference, I don't think, in any of them, except this guy offers more free electronic help than any other author I've ever seen. And this Larson Pre-Calculus 1 is one example of that. It has videos explaining the concepts of pre-calculus. It has worked out solution videos for all the checkpoint problems, which I was just pointing out to you, and then other things. And then we'll be talking later about CalcChat.com and CalcView.com. These are free websites. There's no code required, nothing. Your grandmother can go to it and log into these and look at the videos. There's absolutely no restriction or limitations or anything. You don't need a code, you don't need anything. Just go to the website. So, always, and I suggest, after class, if you have a free period, or maybe you have another class, but the first time you have some free time, try to do every checkpoint that we've done in class so you can reinforce what we did and make it yours. Not just something you're spectating me doing, but you do it. All right. So, moving on to page 263, degree measure. Whew. I mean, radians are fine, but I'm used to degrees, okay? The thing is, in calculus, you're going to deal mostly with radians, okay? A second way to measure angles is called degrees. Now, degrees are actually a unit. A radian is a ratio. It's not really a unit. The degree is a unit, and it's represented by that little symbol. Superscript bubble, like a temperature degree, it's just a degree. And that is a unit. So if you have degrees, they will be denoted by that thing. If you ever have an angle referenced as a number, without that, it's radians. With that, it's degrees. What is a degree? Well, a degree is way smaller than a radian. Remember, a radian is about, you should be thinking of it in this term, but I think of it, it's about 60 degrees. Not quite, close. 57 point something like that. It's close to 60 degrees, but it's not 60. It's not yet 60. Okay? Now, what is a degree then? A degree is tiny because it's equivalent to the rotation of 1/360th of a revolution around the vertex. In other words, 360 degrees makes a whole circle. Okay? So what would make half a circle? 180. What would be a quarter of a circle? 90, right angle, 90 degrees. Okay? That's what degrees are. So a degree is really tiny. A radian's pretty big. Okay? Now, where can we get to 360? I don't know this for certain, but the best I've been able to figure out, there was an ancient civilization in what we may call Mesopotamia, the Tigris-Euphrates Valley. They were called the Sumerians. Lived in probably what is currently Iraq or Iran, that kind of area. They were precursors to the Babylonians, which is basically Iraq today. They used kind of a mixture between a base 6 system and a base 10 system. 6 times 10 is 60, and another 10 times that is, another 60, 6 times that is 360. I don't know how their system worked, but anything that you figured that's a part of, like degrees, or some other things, I can't think of them right now, that are based on that. That is, we can blame the Sumerians for that. Okay, so to measure angles, it's convenient to mark degrees on the circumference of the circle. Okay? Now, like we said, the easiest way, all the way around the circle is 360, halfway around is 180, quarter way around is 90, half of that is 45, a third of that would be 30, and you could do 15s if you wanted to. If you did a 15 here, then 15, 30, 45, 60, 75, 90, you know, you could do it that way, and represent that. Because 30 degrees is 1/12 of 360, and this is 1/12, 1/12, 2/12, 3/12, 4/12, 5/12, 6/12, 7/12, 8/12, 9/12, 10/12, 11/12, 12/12, yeah, that's 360. So that's how you would represent that. 45 is 1/8 of the way. 45, 1/8, 1/4, 3/8, you know, and 4/8, 5/8, 6/8, 7/8, 8/8, and the back all the way. So yeah, that's how we do this. So 60 is 1/6 of that. 1/6, 2/6, 3/6, 4/6, 5/6, 7/6. Okay. However you do it. Now, if you're going to the extent of doing that, you might also want to superimpose on that what our radian measures were. And what's all the way around the circle?
One revolution.
Say again?
One revolution.
That's one revolution. How many radians is that? Two what? 2 pi radians. Okay, 2 pi radians. Halfway around would be pi radians. A quarter way around would be pi half radian, pi fourth radian, pi 6 radians. So you could, for these angles here, you could do it. So this is 30 degrees is pi 6 radians, 45 is pi fourth radian, 60 would be pi third radian, 90 is pi half radian, 120 would be 2/3 pi radians. Yeah, 2/3 pi radian. This would be 3/4 pi radians. This would be 5/6 pi radians. This would be pi radians, and then you go on. So you could assign those popular fractions of pi's to these angles, because we will be using those and referring to them interchangeably pretty much. Okay. So a full revolution counterclockwise, remember we always do that, is 360 degrees. Half a revolution is 180. Quarter is 90. We just don't have that. Because 2 pi radians was your 360, your pi radians is 180, and your pi half radians is 90. So 360 degrees is 2 pi radians. Okay, and here is the best one to hang on to. 180 degrees is pi radians. Now they're writing this, we already said, degree was a unit, so it's 180 degrees. Radians is not really a unit. We use it as if it is, but it's really a ratio. That's equal to pi radians. Now that gives you the means. This thing right here gives you the means to convert any angle degree to radians or any radian degree to angles. Okay? Now they say, remember these. I don't like memorizing. Okay? So here's what I do. This leads to conversion rules in the next slide. I'm going to let you see how they do it, and then I'll tell you how I do it. Okay? So here are your conversion rules. But they're all based on 180 degrees is the same measure as pi radians. Okay? Remember that. And this is how they do it. They say, to convert this to this, you multiply by this. If you convert this to this, you multiply by that. I don't like remembering things like this. I like I do all my conversions pretty much by something. I've heard some people call it the train track method or something like that. I set up ratios, okay? And I'll show you how I do it, but let's first look at their pictures here. To apply these two conversion rules, use the basic relationship, pi radians of 180 degrees. That's the thing to remember, okay? So pi 6 radians is 30 degrees, pi 4th radians is 45 degrees, pi 3rd radians is 60 degrees, pi half radians is 90 degrees, pi radians is there's 1 is 180 degrees, and 2 pi radians is 360. Those are the most common, our favorite angles. We're going to do lots of things with those angles. But to do any angle, you use a conversion. And I'll show you how I do it. Now, but before we do, let's do this. When no units of an angle measurement are specified, you assume that implies radians. So if you do 125, an angle of 125, that's not 125 degrees, that's 125 radians, which is round and round and round. Or if you see theta equal 2, that's not 2 degrees, 2 radians. That's somewhere in the second quadrant. Okay? For it to be degrees, you have to have a degree symbol. Okay? So please, when you're writing an answer, if you're writing the answer in degrees, be sure you put the degree symbol. If you're writing in radians, you don't need a symbol, or you can put RAD or spell out radians. Okay? So here's example 3. Now, I don't like this because they give you the whole problem here. Here's how I do it. It's basically the same thing they're doing, but here's what I do. You have 135 degrees, and you're trying to get it to so many radians. And I'm going to write RAD as if it's a unit. It really isn't. Now, this is how I do all my conversions. I teach physics and in practice physics and physical science, you know. Here's how I do all my conversions. Notice I put 2 blanks here. You really have 2 things here. You have a number and a unit. This blank represents a number. This blank represents units. Equal, number, unit. Okay? And here's what I say to any conversion in the world that you're ever trying to do. Put the units in their place. Don't worry about the numbers. Put the units in their place. Okay? Now, you're going from degrees to radians. So one of those is going to be on top and one's on the bottom. Which do you think is going to go where? You're multiplying here. That's the key. Multiplying by your conversion factor. So what unit goes where? One has to go on top, one has to go on bottom. What goes where? Between radians and degrees. Radians what? Degrees on the bottom. You're absolutely right. And radians on top. Why? So degrees can cancel out and you're left with radians right where you want them, right? So once you put the units in their place, then just match the units with the numbers. How many radians are equal to how many degrees? No? Say that one more time. Okay. There's a relationship to remember. Pi radians is 180 degrees. So you put pi radians here, and you put 180 degrees here. Okay? Now, let's do whatever we can to simplify. Well, I look at these 2 numbers here, and I say, well, I know that 5 will go into each of those. So 5 will go into 13, 2, 7 times, right? And 5 will go into 180, 3, 6, 36. I'm having trouble thinking, okay? Is that right? Yeah, okay. Now, what will go into both 27 and 27 and 36? 9. So this will be 3, and that would be 4. Hey, there we got it. It's 3 pi over 4. 3/4 pi radians. And sure enough, number here, we said, let me go back one more. Okay, here was your 135 degrees, right? There's pi fourths radian, 2 pi fourths, 3 pi. 3/4 pi is 135 degrees. Make sense? And that's exactly what we got. Now we did the same thing they did, but they said, remember this formula. I don't like remembering formulas, but I like to do my unit conversions. All you have to remember is that pi radians is 180 degrees. Hopefully you get that drilled into your head. That's all you have to remember. You don't have to remember which you multiply, which you divide. Just get that, put the units in their place, match up the numbers with the units. You got it done. Okay? Let's see how they did it. I think I'm going to have to erase what I did. Is that okay? Okay. Boy, that's 3/4 pi radians, okay? Leaves a little bit to be desired, I think. So, however you want to do it, you can do it. Okay? The B part. Again, I don't like that they did all the work for you. I like to just play like you can't see this. Let's do 540 degrees. We want to convert that, so there's our 2 blanks for our conversion factor, to so many radians. We're going from degrees to radians. What do you put first? Always put the units in their place. What unit goes where? The second blank. Which all? Yeah, degrees go in the bottom and radians on top. And how many radians are equivalent to how many degrees? Say again? What's the relationship? How many radians or how many degrees? Say again? 180 degrees is how many radians? Pi radians. Remember? Pi radians is 180 degrees. Okay? That's the thing to remember. Now you can cancel out your radians. And this is pretty easy. Let's first get rid of the zeros. You divide both numerator and denominator by 10. Now, what is one factor that will go into 54 and 18? 9. 9 will go into 18 twice. 9 will go into 54 how many times? 6. Well, we can go again, can't we? 2 will go into 2 once, and 2 will go into 6 3 times. You're left with 3 pi radians. Is that right? So 1 pi would be 180 degrees. 2 pi would be 360. Add another 180 to 360. Sure enough, you get 540. 3 pi radians. Make sense? All right, good deal. Let's see if the book got it right. I'm lost here. Oh, there we go. 3/4 pi radians and 3 pi radians. Yep. So let me erase this so you can see them do it. Of course, they don't do very much. They just say it's 3 pi radians. If you see what they're doing there, that does make sense. But I don't like memorizing formulas, but boy, using your unit conversions, put units in their place, match numbers with units, you got it done. All right. They are skipping example 4. So let us do example 4. All right. All right. By the way, example 3 is followed by a checkpoint. The answer to the checkpoint is located at larsonprecalculus.com. Please do those soon after class. Okay. The A for example 4 is you got negative pi fourth, no, pi halves radians. I think you probably know the answer to this without thinking too hard, but let's do our conversion. That negative pi halves radian. Now, what we're going to do is do blank blank equal blank degrees, because you're going from radians to degrees. Okay? I forgot to write in radian. What do you put first? Units in the place, and which one goes where? Radians at the bottom and degrees at the top. And this way the radians will cancel out. And you tell me what we do here. What's the relate? Say again? 180 degrees is the same as pi radians. Perfect. Okay, and here we see we can divide out the pi's, and then 2 will go in 180, 90, so this will be minus 90 degrees. And that's exactly right, because pi halves radians is 90 degrees. Right? Okay. That one's pretty easy. But how about this one? 2 radians. Okay, this is the B part. So I'll multiply that by blank blank to give you blank degrees. What goes where? Radians on the bottom, degrees on top. The radians are going to cancel out. How many degrees are in how many radians, or how many radians, how many degrees? What's that ratio? Say again? 180 degrees is the same as pi radians. Okay? Now, there's nothing you can divide out here, so you're just left with 360 divided by pi. Okay? And if you happen to have a calculator, do that. 360 divided by pi. Say again? I can't hear. It certainly isn't 2. Okay? You're not converting this. You're doing 360 divided by the number pi. Yes, but this isn't radians anymore. We canceled out radians. This pi is just the number pi. 3.1415, okay? Most of your calculators have that key on it. So do 360 divided by pi. What do you get? Approximately. A little louder. 1 what? Okay, my hearing is terrible. 121, I think that's a little too much. 114, that sounds a little bit better, and they actually do 0.59, okay, degrees, okay. It's 360 divided by the pi key, okay. Now, I think that's probably what you get. Now, remember what I said earlier, that pi, that 1 radian was about 60 degrees, a little bit less. Well, 2 radians would be a little bit more or less of 120 degrees. And sure enough, it's close to 115 degrees, so a little bit less. So at least that makes kind of sense. Okay? Okay. There's a checkpoint after that one. Please do that as soon as you can. And the checkpoint answer is at calcchat.com. WashingtonPrecalculus.com. Worked out solution. All right, let's move on to applications. Okay, and this author is pretty good about doing applications as well. Here is our original definition for what a radian is. The radian measure formula, remember the angle, and everybody's favorite angle in the Greek alphabet is theta. So you can use alpha, beta, whatever, but everyone's favorite is usually theta. The theta in radian measures is your arc length divided by the radius. So it's S over R. Now that can be used to measure the arc length along the circle. What you do to get arc length is multiply both sides by the radius. So if you know the radian measure, multiply it by the radius. If you know that, you get arc length. So that's what they've done here for a circle of radius r and a central angle theta. Now that theta has to be in what units? Radians. Remember that. That central angle theta measured in radians. The arc length S is given by S is equal to R times theta.
So you saying theta is always in radians?
And for this formulation, it has to be.
Oh, for arc length.
Yeah, for arc length formulation. Yeah. So where theta is measured in radians. Note that if R is equal to 1, the radius of 1, then your arc length is going to be theta. Now, it sounds weird because you think of arc length as being a length, but it's the same unit of whatever that 1 was. Inches, miles, meters, whatever it happened to have been. Then the theta would be, the S would be whatever radians that was, that's how many of those inches and meters or miles or whatever. The radian measure of theta equals the length of the arc. Okay. Because remember, radian is not a unit, it's just a number. Some real number, radian. And that would be the length of that arc, whatever unit the radius is. If you knew the units. All right. Here is example 5. A circle has a radius of 4. 4 inches. Now, to me, that's sort of gripey, because if it's inches, write down inches. Okay. 4 inches. Circle has a radius of 4 inches. Find the length of the arc intercepted by a central angle of 240 degrees, as shown here. So what we're looking for is the length of the arc, that's the S, of that angle, 240 degrees. So how would you do it? A little louder. What'd you say?
240 equals,
Say again? Say it again? Oh, okay, okay. You're saying S is equal to R theta. Is that what you're saying?
Yes.
Okay. So this would be 4 inches times 240 degrees. That would be 960 inches. 960 inches. If this is 4 inches here, that would be about 4, 8, probably get 960.
I was saying theta equals S over R.
Okay. Okay. But you don't know what S is. That's what we're looking for.
And the radius is 4. So
Say again?
the radius is 4. So S 240 equals S over 4.
Okay. Okay. What I'm hearing is S over theta is equal to R. Is that what you were saying, or vice versa?
I'm not sure.
Huh?
I'm not sure.
Okay. Y'all have a really good idea, but you're missing a real key point. Where theta is measured in radians. You can't use this formula unless your theta is in radians. This theta here is in degrees. So guess what your first step has to be? Yes, you first have to convert that to radians, then you use the formula we just had. Okay? So, how do you convert that to radians? Okay, first put the units in their place, and what unit goes where? Radians on top, degrees on the bottom, then you match the numbers with the units. Second, pi radians is the same as 180 degrees. Okay, now you can divide out the degrees. I'll get rid of the 0 first, so dividing both numerator and denominator by 10. And what would be common between 24 and 18? 6. 6 will go into 18 3 times. 6 will go into 24 4 times. So that would be 4/3 pi radian. Okay. Now you can use your S is equal to R theta. That works now because you're in radian degrees. So that would be 4 inches, that's your radius, times 4 pi over 3 radians. That's not really a unit, but I'll write it down that way. So this would be 16 pi thirds inches. Because radian is really not a unit, it's just a ratio. Okay? 16 pi thirds. So someone with your calculator figure out how long that is. A little louder. Okay. My hearing's so terrible. 16.75 inches. I agree. That sounds like a very reasonable answer. Here's why I say that. Remember what pi is? 3.14. That's a little bit more than 3, right? So it'd be 3 in a small fraction, right? Well, that will almost cancel that out. You have a little left over, and 4 times 4 is 16. That's a little bit more than 1. So yeah, that seems like a very reasonable answer. And then, doing what I was doing before, if this is 4 inches, then that would be 4 inches, 8 inches, 12 inches, a little bit more than 16 inches. Not necessarily precise there. That makes sense. 960 inches? That doesn't quite jive. But this one does. 16.75. Let's see what the book got. They got 0.76 inches. What's that among friends? Okay, about 16.676 inches. All right, and again, there is a checkpoint right after that. And that checkpoint can be checked out at larsonprecalculus.com. Okay. Let's see. Let me erase my scratch here so we can see what they do. Oh, they went to a new slide anyway. The first thing they did, because the formula you want to use only works for radian measurement. So first get the degrees to radian, just like we did, and that gave them 4/3 pi radians. And the S equal R theta would be 4 times 4/3. So that's about 16.76 inches. Notice that the units for the R determines the units for the arc length, because theta is in radians. That's a dimensionless unit. It's just a ratio. So whatever unit you had for your radius, that's going to be the same unit for your arc length. And they say theta is given in radian measurements, which has no units. So ratio, we write it as if it's 4/3 pi radians, but it really has no units. Now, bottom of this page, here's another application. The formula for the length of a circular arc can now help you analyze the motion of a particle moving at constant speed along a circular path. And this is going to relate your linear speed with your angular speed. What do we mean by linear speed? That would be how many inches per second, meters per second, millimeters per second, miles per hour, whatever. That's what we mean by linear speed. What length per time, okay? Whereas angular speed is what angle is being cut per unit time. That could be degrees per minute or radians per minute. Most of the time it's going to be radians per minute or per hour or per second, whatever. The same per that you use for this, if it's per minute here, it would be per minute there. This would be inches per minute, that would be radians per minute. Okay. So, consider a particle moving at a constant speed along a circular arc of radius r, whatever that is. Okay. If s is the length of the arc traveled in time t, then the linear speed would be s divided by t, because that's how far it traveled in that time. Linear speed v of the particle would be the arc length s divided by the time t. And again, that would be inches per second, meters per minute, whatever it happens to be. Moreover, if theta is the angle that it's doing, guess what? In radian measures, just about every formula we will have will assume the angle is in radians. Okay? If theta is the angle in radians corresponding to the arc length s, then the angular speed, now that symbol there is a lowercase omega. Okay? Omega And the uppercase is the thing that looks like an upside down horseshoe, but the lowercase is this thing that looks like a W. Lowercase Greek letter omega. Angular speed, that is in radians per time. Okay? Greek letter omega of the particle is omega is equal to how many radians per time? Radians per second, radians per minute, whatever. Now, I want to remind you of something here. What is the formula for arc length? The S. R theta, where theta is in radians. So that'd be R theta over T. So this would then be R, and if theta over T is omega, that would be R omega. Okay? Now I'm doing that for you here because the next example they give, they go around their elbow to get to their nose. Okay? And it's so much easier to use that. Okay? So linear speed is R times the angular speed. It just works out that easily. Okay? Now, here is a definition. Oh my goodness. That definition is a page away. Let's go back and do example 6. Okay? We will use the linear and angular speeds here. The second hand of a clock is 10.2 centimeters long. Shown in the figure there, but I'll let you look at the figure. Well, y'all don't have a book, do you? I'll try to draw the figure. So here's the face of a clock. Not a very nice face. It should be rounder than that. And here's your second hand, and that second hand is 10.2 inches, wasn't it? No, centimeters. Okay, 10.2 centimeters. Find the linear speed of the tip of the second hand as it passes around the clock face. So we want the linear speed, which is our velocity, v. Okay? Now, anyone remember how you get that? It's distance over time, s over t. That's what your linear speed is s over t. Okay? Just as a right there. Linear speed is s over t. Okay? Okay. Now, we're talking about the tip of the second hand. Okay? What is the arc length cut in a given time? What time would be a convenient time to use? Remember, that's the second hand. Say again? Okay. This is the radius, and what we want is an arc length. Now, because it's the second hand, it's moving clockwise, but it's just a length. 12 watts, 12 centimeters, I don't know. I would say let's do the whole length around there. And how far is that? 360. Say again? 360. That's degrees. That's not a length. Say again?
2 pi.
2 pi radians, you're absolutely right, multiply that by, because we know this from before, S is equal to R theta. When theta is measured in radians. Your radius is the 10.2, and you just told me that was 2 pi, so this will be 10.2 centimeters times 2 pi radians. Now I'm going to put RAD, but that's not really a unit, right? So that's going to be 20.4 centimeters, pi centimeters. Everybody agree with that? Yay? Okay. So that's how far it traveled one trip around. How long did it take to go one trip around your clock face? That second hand. Think? Say again? Okay. Let's just think about a clock. How long does it take that second hand to make one trip around? Second?
12 hours.
The second hand.
60 minutes.
Second? 60
seconds.
seconds. Your minute hand, 60 minutes. Yeah, okay. The second hand goes around in 60 seconds, right? 1 second, 2 seconds. 60 seconds, 1 minute. Move minute hand, 1 space, right? So that is in time of 66. So here we have a V is equal to S, which is 20.4 pi centimeters divided by 60 seconds, right? That's how far it traveled one time around, and it took it 60 seconds to get there. Or you could have put 1 minute if you wanted to. That would have worked too, but I think they give their answer in, so many per seconds, okay? Again, pull out your calculator and see what this gives you. 20.4 pi times pi divided by 60.
I know 1.06.
1.02 units would be centimeters per second. That is the approximate. Now they got 0.07. Oh, say again?
Maybe it was round then.
I can't hear.
They had the round then.
Yeah, okay. 0.7. Okay. Centimeters per second. Okay? That's how fast it's moving if it's a 10.2 centimeter second hand. If it was a shorter one, it would be going slower. If it was longer, it's really flying. The tip has to be moving much faster. Okay. So 1.07 centimeters per second. There is a checkpoint. Please do those as soon as you can out after you finish class. I wish we had time in class to do all the checkpoints too, but no way. Okay. Let's do example 7. Everybody got that one? 6? Okay. Example 7. Why did I write the formula? It was right there in front of me. The blades of a wind turbine, I'll try to draw this. Here's the wind turbine. Okay. This is the base of the wind turbine. Okay, and those are the blades. The blades of a wind turbine are 116 feet long. Okay. The propeller rotates at 15 revolutions per minute. 15. Quite often we call it RPMs, right? Well, what that means is 15 revolutions, REV, per minute. Okay? That's what they tell you. All right. The question is, find the angular speed of the propeller in radians per minute. So what we want is the angular speed. Does anyone remember what the symbol for angular speed was? Omega. So that's your omega. That's what we're looking for. What is the angular speed of the propeller in radians per minute? Okay. Now, here we have to sort of do some thinking on here. If this is 15 revolutions per minute, but we want our omega in radians per minute, what we have to come up with is how many radians are in a revolution. And a revolution is one time around. How many radians are in that? 2 what? 2 pi radians. So you multiply the 15 by 2 pi, and you get 60 pi radians per minute. Okay, that is your omega. Agreed? Wait a minute. No, I can't multiply. 2 times, I multiplied and then multiplied. That would be 15 times 2 pi is 30 pi. Duh. 30 pi radians per minute, because 2 pi times 15 is 30 pi. I multiplied it and then multiplied it again. So that's 30 pi radians per minute. That's the A part. The B part is find the linear speed of the tips of the blade. Now, oops. Ha, this is what. The linear speed V, okay, V is equal to the arc length, if you wanted to do it that way, S over T, okay? And your S would be your, from here, r theta, and our theta is in radians per minute, so you're able to do that, r theta over T, right? Because S is equal to r theta. Okay? But this thing right here, that is your omega. So this is the r omega, right? So, we know what our r is. 116, I can't write, feet times your omega, which is 30 pi radians per minute. But remember, radian is not a unit, it's just a ratio, it's dimensionless. So this would be, trying to do it in my head, 348, is that right? Pi feet per minute. I believe that's right. So what is that? 740?
3480.
I can't. Oh, 748. Is that what you said?
No, 3480.
80. Oh, okay. I forgot my zero. Yeah. Whoa. Sorry. My pen gave out on me. Okay, there it is. 740. Why won't that do? Okay. Okay, there we go. 7. Wait. Is that what you said?
Mm-hmm.
Yeah. 3480 pi. Okay, yeah. Okay. Now, take that and multiply that number by pi and see what you get. I forgot the zero there, you're right. Anybody get it? 3480 times pi. It's a big number.
1107.7.
11 Whoa. You keep getting a little bit bigger than the book gets. How do you do that? Okay, this has some serious problems. Huh? Say again?
10,932.
Now that sounds better. Okay. Okay, say it one more time. 10,933. 32. Well, the book rounded to 33. Excuse me. Have to make sure y'all are awake. Okay. Feet per minute. Okay. Now, that sounds pretty fast. Guess what? It is. If you have seen those wind turbines, we don't have many around here, but if you have seen them, they whistle. They are moving very, very fast. That's why some people complain that birds, if they're happen to be flying by and they're moving real fast, usually they'll stay away just because of the noise. But if they do happen to fly through, you have mincemeat. Okay, I mean it's no longer birds. A pile of feathers. Okay, and there is a checkpoint right under that. Did y'all start packing for a reason? It's what? 11 what? I can't. 11:17. So we're 2 minutes over. No extra charge though. Okay, so let you get by. We'll start next time with the area of a sector of a circle, the definition of sector of a circle, and we'll start with the area of that. Okay, so that's on page 266. Homework exercises on 267, 8, and so on. Do either 7 or 9. They're both at calchat.com. That's the other website I was telling you about. 11 has 2 parts. It's at calchat.com. 13 has 2 parts. It's at calchat.com. 15 has 2 parts. It's both at calchat and calcview.com. 17 or 19, they both have 2 parts. They're both at calchat. 17's at calcview. 21 or 23 are both at calchat. 25's at calchat. 27's at calchat. 29's at calchat and calcview. 31 and 33 are both at calchat, but 33's at calcview. 35 is at calchat and calcview. 37 is at calchat and calcview. 39 and 41 are both at calchat. 43 and 45 are both at calchat. 47's at calchat. 49's at calchat. 51's at calchat and calcview. By the way, 47 and 49, they didn't do any examples like that in the book, so you might want to check those out, and if you have trouble with them, ask, and we'll do those in class. Okay, 53's at calchat, 55's at calchat, and we'll stop there because that gets into the sector of a circle. Yeah, so we'll stop at 55. We'll pick up the rest of those next time. All right, any questions? All right. Good deal. Have a good weekend, good holiday weekend. Y'all do know the good news, bad news situation, right? The bad news is there's no classes on Monday, right? It's a holiday. But the good news is it doesn't affect us any. We meet on Tuesday and Thursday, so we won't miss a class. All right, good deal. All right, we will see you on